All right, moving on to 7.3. This is a new kind of U substitution. It's called trigonometric substitution, or trig sub. And it works on very special kinds of antiderivatives. So it's another way of finding the antiderivative. This is an example here. I think it's number 2 since we did a little bit of 7.2 before, but it's example number 2 for today. And it's the integral of the square root of 9 minus x squared, all divided by x squared dx. Okay, so when you see the square root of a number plus or minus x squared, then it's supposed to remind you of, what's the picture? A right triangle, what I've pictured on the right there. So it's supposed to remind you of the Pythagorean theorem. Now, after this point, you can work it out, or you can memorize some of these triangles. Easy enough to double check. You have to make sure that they obey the Pythagorean theorem. So what we do is we draw a triangle that has one of the sides the square root of 9 minus x squared. Then if I make the other sides x and 3, it works according to the Pythagorean theorem. If you square the two sides, you cancel that square root, so you just have 9 minus x squared. Then you add the square of the other side, so you add on x squared, which cancels the negative x squared. That leaves us with 9, which is exactly equal to the hypotenuse squared, 3 squared. So yes, we'll draw some of these triangles that always work, and you can memorize, but then you can always double check that they obey the Pythagorean theorem. Now once you have the triangle, you pick one of the angles, not the 90-degree one, but one of the other angles, theta. Either will work, but I picked this one because I wanted to use sine first. And I'll use sine because sine of that angle theta is the opposite over the hypotenuse, x divided by 3. You can write that down if you want. Sine of theta equals x over 3, but I wrote x equals 3 times sine theta. I multiplied through by 3, so I moved the 3 up. X equals 3 sine theta. And that's the U substitution equation. Because now I find dx d theta. I take the derivative of that x with respect to theta, and it's 3 cosine theta, and I move the d theta up to the other side, went ahead and did that. And now I'm ready to do substituting. I look back at my original problem. I have a dx, and I have a bunch of things with x squared in them. So I'm going to need to substitute in for x squared. So back on the right, I can just square both sides. If x is equal to 3 sine theta, then x squared is 9 sine squared theta. All right, that'll take care of the denominator. Then on the numerator, I have the square root of 9 minus x squared in my original integral. There's 2 ways to do that. One is, now that I know what x squared is equal to, I can plug in there, that's the algebra in the farthest green box, and work it out algebraically. I'll show you how that works. You plug in 9 sine squared theta, factor out a 9. 1 minus sine squared theta is cosine squared theta, the Pythagorean identity, and then square root of squared gives me back cosine theta. It's not too bad, but it takes a few steps. Or, for the numerator, you can look back at that triangle and you get the same answer. In the triangle, the square root of 9 minus x squared is the adjacent side. So if I want to use the adjacent side, I could say cosine of theta is equal to square root of 9 minus x squared divided by the hypotenuse 3. And then multiplying through by both sides by 3, I get that same equation. 3 cosine theta is equal to the square root of 9 minus x squared. All right, now I can look at the original integral and replace everything so that there are no more x's, only thetas. The top numerator is 3 cosine theta. The bottom x squared is 9 sine squared theta. dx is 3 cosine theta, d theta. At first it looks worse, but a lot of stuff cancels. 3 times 3 is 9, which cancels with the 9 on the bottom. And I'm left with cosine squared over sine squared, which is cotangent squared, because cosine over sine is cotangent. And then cotangent squared minus is equal to cosecant squared minus 1. That's another version of the Pythagorean identity for trig. And that's stuff that I know how to integrate. the antiderivative of cosecant squared is negative cotangent theta, and the antiderivative of -1 is negative theta. Now remember, this is because I'm integrating with respect to theta now, so the 1 becomes theta and plus c. But then to finish, you substitute back in. There's a couple of ways to do that. If you have a trig function of theta, you can look back at the triangle. Cotangent is cosine divided by sine, since it's 1 over tangent. Or since it's 1 over tangent, it's adjacent over the opposite. So it's, back up, square root of 9 minus x squared divided by x. And that's what we put in. Now, theta by itself, I need to replace it. That I can look back at my substitution. If x is equal to 3 sine theta, I can solve that for theta. Divide both sides by the 3, and then take the inverse sine of both sides. So theta is equal to sine inverse of x over 3. And that's the final answer.